Hello everyone, welcome back. Today we're going to be talking about exploring the paradoxes, right? So the different paradoxes that occur with using Hamilton's method. We're going to look at those in detail today, and I try to come up with some easy to follow examples that demonstrate the three different paradoxes mentioned in the notes. So we're going to start off right away here with what's called the Alabama paradox. And so we've got a situation here where we've got essentially got three states, right? They're classes, they're math classes, but we're going to pretend like they're states, like in the other examples, okay? So in our table here, I'm just going to go CA for college algebra, stats, and liberal arts math, okay? And then we jot down their populations. So we got 978, 500, and 322. All right, so the next thing we need is a divisor. So I'm going to add up my total population here, right? So 978 plus 500 plus 322, and you should get a grand total of 1,800 students. And it looks like we're going to hire 30 teaching assistants. So we take 1,800 divided by 30. And we should get a divisor of 60. Okay. So to get my quotas, I'm going to come over here and I'm going to divide each of these by 60, and we should get these numbers. So you should get 16.3, 8.33, and 5.367. Right, and I'm going to put a 0 here. You notice that these decimals do get kind of tight here, like they're all really close to each other, which is why we like to make sure we carry enough decimal places so that we can see who has the larger decimal portion at the end. All right, so our initial apportionment, according to Hamilton, Hamilton told us to ignore the decimal parts first and do an initial apportionment. So we're going to do 16, 8, and 5. And if I add those up, that gives me a grand total of 29 teaching assistants. But we need to apportion 30. So we have one bonus teaching assistant that needs to be apportioned here, and it's going to go to language arts math, which has the largest decimal portion after the whole number. So we're going to go 16, 8, and 6, which gives us a grand total of 30. Okay, so there we go. We did a Hamilton apportionment. Now, what happens? Okay, so where does this problem occur? Well, we have to pretend that instead of 30 teaching assistants, let's say we decide to hire one more. So we're going to increase the number of assistants, or the number of things that we need to apportion, to 31. Okay, so everything else stays the same, right? So we have college algebra, we have stats, we have language arts math. All the populations will stay the same, so I'm just going to copy those down here. And this time, when I go to calculate my divisor, right, we still have 1,800 total students, but we're going to divide by 31 this time, and we get a new divisor. Our new divisor is going to be 58.0645. All right, so I'm going to take that 58 and I'm going to come over here to my population, and I'm going to divide each of my three states here, or my three classes, by our new divisor. Okay, so here's my first quota. We get 16.843. We get 8.611. And then we get 5.546. Then we do our initial apportionment the same way. So we're going to go 16.85. And then we tally that up, right? So 16 and 13. All right, gives us a grand total of 29 again. So this time we're going to have two bonus teaching assistants here, because we have to get up to 31. So the highest decimal portion goes to college algebra, which will increase to 17. And then the next highest goes to stats, which will go up to 9. And then language arts math will be at 5. Okay. I'm going to grab my highlighter here because I want to demonstrate what happened and where the issue is occurring. Before, when we had 30 teaching assistants, language arts math got 6 of the teaching assistants. When we increased the number of teaching assistants to 31, language arts math went back down to 5. So by increasing the number of teaching assistants, we actually screwed over language arts math and caused them to lose one of their teaching assistants. This shouldn't happen, right? So it's almost like those fairness criterion, like that's not fair, that shouldn't happen, but under Hamilton's method, it does. And it happened to Alabama, and they got really upset about it. All right, so they did not like that they lost a seat because they increased the number of representatives in Congress. It was a huge ordeal. All right, so the Alabama paradox occurs when you increase the number of things that you're apportioning, and somehow someone loses one of their representatives. Okay, that's the Alabama paradox. All right, the next one we're going to demonstrate here is what's called the population paradox. And the population paradox occurs when the populations of our states change, right? So what we have here, we have a small country. They have 24 seats that we need to apportion, and we have two different apportionments that we're going to do, one for the 1990 population and one for the 2000 population here. All right, so let's do the first one. We've got A, B, C, and our population in 1990 right here across the first row. So we got 530, and we've got 990, and we got 2240. Okay. And I was even nice. I totaled it up for you here, so I'm going to take that 3760 and I'm going to divide it by the 24 seats we need to apportion. Okay. And you should get 156.67. Now we go through our individual populations and divide by the divisor. So our first quota should be 3.38, then 6.31, and 14.298. Okay, I carried 3 decimal places there. Because again, the decimal values are getting pretty tight, so I want to make sure that I can distinguish here. So the initial apportionment is going to go 3, 6, 14. You'll notice I'm trying to go through these pretty quick, and Hamilton should go pretty quick. It should be pretty simple. So 3, 6, and 14, 9 and 14 is 23, and we need 24. So there is a bonus seat here that we need to give away, and it's going to go to state A. So they're going to go up to 4. The other two stay the same, and now we have 24 representatives apportioned. So remember those numbers, 4, 6, and 14, and you're probably guessing what's going to happen somehow someone is going to lose something that shouldn't have. All right, so let's see what happens here. Okay, so now we're doing the 2000 census, right? 10 years has passed by, and we still have 3 states. We still have 24 seats for Congress, but the populations over the years have changed. All right, so our new populations are going to be 680, 1250, and 2570. All right, so as you would expect, all their populations went up. All right, now we go and we calculate our new quotas, right? We would tally these up, and you should get 4,500. And we would divide that by the 24 seats that we need to apportion. So you should have 187.5. That's going to be our divisor. So we take our divisor, we're going to divide the populations by the divisor and see what we get. So we got 3.627, 6.67, and 13.71. All right. Initial 3, 6, 13. And when I add those up, I do get 22, sorry. Can't do math. And then we're going to go ahead, and it looks like we got to give away 2 bonus representatives, so that's going to go to C and B. Yep. So we go 14, 7, and 3. Okay. All right, so it looks like State A lost, a representative here, and I don't know if that's really a problem or not yet, because you could lose a representative if your population changes or it doesn't grow fast enough. And other states grow faster than you, then they're going to end up getting more representatives to represent the increase in their population. So one of the things that we need to do to analyze whether or not there is actually a problem here is we need to look at the percentage increase for each state. All right, and I'm gonna spare you. I'll do one of the calculations, so that way you can see how to calculate a percentage increase. But I'm never gonna ask you to do this on a test or a quiz here. Okay, so for instance, if I wanted to calculate the percentage increase for state A, I would take our current population, which is 680, and I would subtract away the 1990 population, which was 530. So we had an increase of 150 people in that state. So to get the percentage increase, we take 150 and we divide by 530, which was the population in 1990, because we want the increase from 1990 to 2000. Right? And if I divide those two, we get 0.28, which is a 28% increase in population from 1990 to 2000. Okay? And that is for state A. If I do the same calculations for the other two states to calculate their percentage increase, state B had a 26% population increase, and state C had a 14.7% increase in population. Now that's a problem, right? Because state A had the fastest rate of growth, and yet they lost a seat. Okay, and the state B here didn't have nearly as fast, or well, they were pretty close, but they didn't have as fast a rate of growth, and somehow they gained an extra representative. All right, so this happened at a point in our history as well with this, and they called this the population paradox, and most people thought that was not fair. That shouldn't happen. All right. Like I said, the population paradox, I'm not going to have you calculate the percentage increase on anything like that, so don't worry about that too much. Just know the situation, okay? So like if I were to describe a situation that was similar to this, make sure that you can name that as the population paradox, all right? Now the last one, okay, is called the new states paradox. All right, so let's suppose we have a certain city that has two districts, A and B. The populations of the districts are given, and we have 100 police officers, and we need to make sure that they are spread out accordingly between the two districts to patrol those two districts. Right? So we have State A, or District A and District B, and District A has 1,045 people, and District B has 8,955 people, for a total of 10,000. Right, so that's a total population. So I'm going to calculate my divisor, right? We take that 10,000 and we divide by the number of police officers that we have hired, right? So that's going to be 100. So when I divide those two, we should get a divisor of 100. Right, so each police officer should essentially be responsible for patrolling 100 people. That's what that is telling us. So now I'm going to go up here and I'm going to say, okay, well, if I divide this by 100, I should get 10.45. And if I divide this one by 100, I'll get 89.55. And then Hamilton says, ignore the decimal part. So we got 10 and 89, which is a total of 99 cops. And then we look at the decimal portions to see who gets the bonus cop. Right, so that's going to be the 55, 89 bumps up to 90, and now all 100 are apportioned. Right, seems great. We got a fair number of cops in each district, and now we are going to change things up, right? Because that's what causes problems. So now let's say the city expands to cover a new district. You start to see why they call this the new states paradox. So remember, we only had districts A and B before. Now we're introducing a third district, and as a result, the city has agreed to hire 5 new police officers. So we added a new state and we added new police officers. Okay, so those two things changed. So we still have states A and B, but now we also have state C. The populations stay the same, and we have to recalculate our divisor. So when I add these up, we get 10,525, and I'm going to take that 10,525 and divide by the now 105 police officers that we have hired. So we should get a divisor of 100.2380. Okay. So we go through and we do our divisions, and we should get these quotas. Go. So we'll Hamilton this, and we will get rid of those decimal parts. So we should get 10, 89, and 5, which gets us a grand total of 104 police officers apportioned. So we do have one bonus cop that we need to apportion, and that's going to go to State A. Right, so State A is going to go up to 11 because they had the biggest decimal portion, and then we have 89 and 5. And now we have 105 apportioned, and you probably saw the problem right away, and I'll highlight that for you. Highlighted here in green. Right? So State B used to have 90 cops, but when we added the new district and 5 new police officers, they lost one of their police officers. Okay, so this is called the new states paradox. New states occurs when you add a new state and more representatives. Okay, and yet someone loses something. Shouldn't happen, right? All of these incidents have occurred at some point in history, in some point in our country's history, which is why the Alabama, or not the Alabama paradox, but why the Hamilton method was finally abandoned and never used again, and it'll probably never be used again. We have a pretty good system now, and we're going to get to that one soon. All right, guys, that's it for today. Good luck. Try the practice problems. Let me know if you have questions.